Good afternoon. I'm Avishay from Straddle. I'm leading the storage management effort in the company, and my colleague Shimshon is leading the HA effort. And together we're going to present how to deploy Cinder, specifically in a highly available manner. So we want to deploy Cinder in a way that's also scalable, also resilient to failures. We want to have limited downtime for users and reduce admin intervention. And there are many, many resources online for how to deploy OpenStack in a highly available manner. There's one link here. If you do a quick Google search, you'll find tens more. This isn't a workshop about, have a safe drive. This isn't a workshop about, just type in this, type in that, and, you get Cinder HA at the end. It's more about understanding the technologies, understanding the architecture, and seeing how it all comes together. So what do we cover today? First of all, what is Cinder? There are some common misconceptions. We'll straighten everything out. How is it designed? And we'll focus on how the design impacts the deployment. So how does the design impact the HA deployment? How can I best deploy Cinder today? We'll stop for a live demo in the middle, where we'll show all the cool technologies that we have. And everything, I'm going to speak about Cinder specifically because I come from the world of Cinder, and that's what I understand the most. But Cinder is a spin-off of Nova, and Neutron is also a spin-off of Nova. And a lot of these core OpenStack projects have the same architecture, so most of what I'll say about Cinder can be applied to the other projects as well. Okay, so a couple quick words about Straddle and Shimshon and I. So we're both in R&D in Straddle. I am a former Cinder core member as of 2 weeks ago. We do hyper-converged infrastructure. We're a software company, and we do it all from compute, where we have customized KVM and Docker, to storage, where we have our own distributed block storage solution and storage management. Network full-featured SDN. We're based on OpenStack. We use several OpenStack components. And our product is easy to install and upgrade in very limited maintenance. And if that sounds good to you, we are hiring. OK, so let's start with what is Cinder. Cinder is basically, like most of the other OpenStack projects, it's an abstraction over a set of drivers. So in the block storage world, you have many, many different vendors. Cinder supports, I think by the end of Liberty, it'll be over 60 different block storage drivers, and with one common northbound API. So that's the real that's really what Cinder gives you. You want to create a volume on your EMC storage, you just do create volume in Cinder, and the command will be routed all the way down to the EMC box, and you'll have your volume there. And next you want to do it on your IBM box, so the command will be routed there. And when you list your volumes, it'll show you all your volumes from all your different storage in one screen. So it's a nice abstraction, and it enables, and the key word is it enables connections between Nova and the storage. So that's a common misconception, that Cinder is not on the data path at all. Basically, you have your storage. Cinder will communicate with the storage and give it information about which Nova host currently wants to connect to the storage to a given volume. Cinder will do whatever it takes to make that happen and pass information about the storage back to Nova. And then Nova will communicate with the storage directly. So Cinder is not involved in the I/O path at all. So let's look a little bit at how it's architected. As I said, many of the OpenStack projects have a similar diagram. So all the way at the top, we have a client, which is a totally separate repository of code. It's not part of Cinder itself. It's not mandatory. It communicates with Cinder's API with a REST interface, which means you can write your own client. You can use whatever REST client you want to use, and you can talk to Cinder's API. The Cinder API is a pretty lightweight process. It basically does some preliminary checks to make sure that the command you want to run can succeed. And then it passes on the command to other processes. So the first one I'll mention is called Cinder Scheduler. You might guess what it does. Schedules? No, it does placement. So any new create volume command goes to the Cinder Scheduler. The scheduler will decide, based on some algorithm, on which backend to place the volume. So you don't necessarily have to say, I want to put this volume on my HP storage. I'll give everyone mention. You can say, I want to put it on any storage you decide. Or you can say, I want it on storage with this specific quality of service level, or storage that's compressed, or whatever parameters you want to give. The scheduler will find a backend that suits what you want, or will return error. And then all the commands end up in Cinder volume, which is does the main work here. Cinder volume talks to drivers. As I mentioned, there are about 60 drivers in Cinder right now. And you can have many instances of Cinder volume, one for each driver, or you can have one instance managing multiple. The driver talks to the storage with whatever protocol the storage talks. It could be SSH or REST or any proprietary protocol for managing that storage. And there's also a Cinder backup service, which this actually does have a good name. It backs up the volumes. It also has drivers. The most widely used one is the Swift driver. So it basically takes a volume, breaks it into chunks, and writes it to objects in Swift. But there are also some proprietary drivers there. And we have the database. So the database holds all the metadata. Which volumes are present, which snapshots, different types of volumes. That's what the Cinder scheduler takes. And all of the metadata about everything is stored in that database. And then we take this whole thing and we say, okay, we want to deploy it. And it's not so easy. And we want to deploy it in a highly available fashion, which is even harder. So what do we have to do? First of all, we have to make sure that the storage is highly available. We have to make sure that the database is highly available. I didn't mention, but all of these components interact via RPCs. That RPC infrastructure also has to be highly available. And then the services themselves, the processes. So we'll start with the storage. We'll go kind of bottom up. So the good news here is that almost all of the storage that is supported by Cinder today is highly available by design, by just natively. You spend several $1,000s at least on some storage appliance. You better hope that it's highly available, right? And most of the storages are appliances. There are also things like Ceph, which is, of course, highly available, Gluster, which is highly available, and others. There are two exceptions that I'm aware of to this. The first is the LVM driver. And that's the driver that's the CI of Cinder, the continuous integration, has always used. And some have deployed this in production, but it's mostly used for development. Basically, it just sets up an iSCSI target over LVM, Linux's logical volume manager. And if LVM is residing on one disk, then obviously if that disk fails, your data is gone. Similarly, there's an NFS, like a generic NFS, which uses the Linux native NFS server, which has the same problem. If your disk goes, or if your server goes, then your data is gone. But however, even if you do use one of these fancy storages that cost thousands of dollars, you have to make sure that you have redundant network paths from each of the Nova compute nodes to that storage. Because the data will be going from the Nova compute nodes to the storage, not necessarily from Cinder. Cinder does do a few things on the volumes and accesses of them, so it does need connectivity to the storage, but mostly Nova compute nodes need that connectivity, and that connectivity needs to be highly available and redundant. Okay, so we'll move to the database. Shimshon will take over.
Thanks, Avishay. So you might think I'm the one standing between you and lunch, so I have good news and bad news. The good news, I have only like 3-4 slides, and then the other news is that Avishay follows with some more slides. But they're really interesting, so it's worth. So Avishay spoke about the storage part that has to be highly available. We also have a couple other components, as we saw before, that have to be highly available, and one of them is the database. So basically, there are a couple of solutions to make the SQL database that's used by OpenStack highly available. It's, as you see here, it's used for all the metadata. So for example, Cinder uses it to keep information about volume, snapshots, etc. Keystone uses it for the different users and tenants, Nova for the different VMs and their status, and so on and so forth. So we don't want this database as a single point of failure, obviously, and there are a couple of different solutions out there to achieve high availability with your database. One of them is to use asynchronous replication of your database. I think MySQL has internal replication that can handle that. The problem or the con for such a solution would be that it's active-passive, so you might miss a few syncs, which has its disadvantages. I think the most widely used solution that we've seen around is using a Galera cluster over either MySQL or MariaDB, which is a fork off of MySQL or Percona. And that basically gives you an active cluster of a couple of instances of your SQL DB. And then you achieve high availability. All the writes go to all of them. You can read from any of them. And this is very convenient. And then another solution, there's of course PostgreSQL replication. Another solution is not to replicate the database in the database layer, but rather put the database on a replicated block device, such as a DRBD backend, and then you get replication on that. I think the OpenStack high availability guide recommends that as at least one of the alternatives. There is another very interesting project which we saw recently by the YouTube folks. It's called Vitesse, and it's basically a SQL architecture that's optimized for scale out. So it's very good if you want very large databases, and it shards them in an optimized way and makes sure that you don't have redundant traffic over the network for every little write, manages caching and stuff like that. We didn't see a lot of support from the OpenStack community so far for it. It might go big, we don't know yet. So that was the database. In addition to the database, as Avishay presented before, we also have our messaging and our RPC infrastructure. We also want to achieve high availability with that. So OpenStack, Cinder, as part of OpenStack, as you know, uses Oslo messaging as a generic layer that abstracts different types of message queues below. And I think the most widely used one in OpenStack deployments is probably RabbitMQ. It's an implementation of the MQP protocol. The default setup of RabbitMQ has all the queues located on one node, or what they call broker. It's obviously problematic if you want to talk about HA because you have a single point of failure. But RabbitMQ also has HA modes, which allow multiple brokers. It has some nice features of linear scalability, where as you're adding more nodes to your system, you're getting more and more queues, and it's distributed better around your cluster. The other option, which is also very widely used with OpenStack, is Cupid. It's another implementation of AMQP. I think from what we've seen, it has not as good support for HA as RabbitMQ does. I mean, their solution for HA is more based on active-passive rather than active-active, which has its disadvantages. Another interesting contender, if you want to make your messaging highly available, is ZeroMQ. So ZeroMQ's, I think, the biggest advantage of it is the fact that it has very, very good performance. So the throughput and latency you're going to get are probably much better than what you'll get with the others. And you could work in a broker-based mode. Usually people like to work in brokerless, especially if you're talking about high availability. ZeroMQ has other disadvantages. I mean, there's never a best option here. And I think I'd say there are probably two problems here. The biggest is that there is not wide support in the OpenStack community for ZeroMQ. So we're seeing most people using RabbitMQ and Cupid, and if you want to start, and I'm saying this from personal experience, you want to start implementing or connecting ZeroMQ to your OpenStack deployment, you'll bump into different bugs that just still haven't been fully fixed by the community. But on the other hand, as I said, there's the performance advantage. After you got high availability on your database and on your storage, of course, and on your messaging system, you need some kind of framework to tie it all together. And we found this very nice, very interesting open source project called Consul, which you might know by a company called HashiCorp, which has a couple of very useful features. One of them is service discovery. So what Consul does is basically it runs a local DNS server on each of the nodes in your cluster. So say you want to access the OpenStack Cinder API service. Instead of accessing by IP, so if you have your default OpenStack setup, you have the controller, and all the nodes know the IP address of the controller, and that's how they access Cinder, because Cinder API is running on the controller. Now, you want to achieve HA, so Cinder API might be running on one node, and then that node might have failed, and Cinder API is now running on a different node. You want to access these guys by names, right? So you have a local DNS server running on each of the nodes. It answers DNS requests, it has a REST API as well. And what Consul does is it enables health checking of the different, or health monitoring of the different services running in each of your nodes. And then if a service is healthy on that node, when you query in your cluster for OpenStack Cinder API.service, and we're going to see a demo of that in 2 seconds, then you're going to get routed to the IP of the node that currently runs Cinder API. If you have a couple instances of your service running, for example, if you have a Galera cluster replicating your database and you have, say, 3 of them running, if one of them is not working, then DNS will not be resolved to that node. If you add another one somewhere else, it's going to resolve that. We're going to see a cool demo of that soon. Another very useful feature of Consul is the key value store. It has a distributed key value store. It works on top of various consensus algorithms. It's distributed, and you can basically access it from any node in the cluster. And it's very useful for managing registry and things like that. There are other solutions. We won't go through all of them, but etcd, Zookeeper, Pacemaker, all give similar functionality, each with their, of course, advantages and disadvantages. So after talking about the different building blocks, I'd like to present what we chose as our solution. And we're a very dynamic startup, so if we meet again in like a year or so, we might be presenting something totally different. But for now, this is what we found to be working best for us to achieve high availability. So we have our OpenStack services that we take, and beneath them, you could say we added our layer of distributed cluster management to make it highly available. So for messaging, I said before we chose RabbitMQ because of its wide support and because of its reliability and I think good fit for high availability. We're using MariaDB as our database, and we're clustering it with Galera. We'll see a demo of that soon. And then we're seeing Consul, as I said before, for service discovery. And of course, needless to say, we're using our storage backend, our proprietary storage backend, which is highly available and addresses that aspect too. So I'd like to move on to the demo, with your permission. Hold on. So what we're seeing here, okay. Can you sort of see what this says? Not yet. So I brought up, back at our lab, and I'm remotely connected to it, a cluster of 5 nodes running OpenStack. The top left one is the controller, but as you can imagine, when we're entering this world of high availability, the word controller is getting more and more meaningless because we can have our services running anywhere in the cluster. But anyhow, the top left one is where we start as the controller. And I have SSH open to 3 other nodes in the cluster. There's another one which I didn't connect to. I can show you, for example, since we're using Consul. Oh, even better, everything's falling apart at the same time. Why don't we do this? Avishay, you want to continue with the slides while I bring up the demo back? Because we might have been disconnected for a second. And then I promise we'll do this demo very soon. Excuse me for that.
Okay, so while Shimshon is setting up the demo, we're going to have Captain Picard here, our sysadmin. We're going to look at some example command flows in Cinder and how they work and what goes wrong. So you want to create a volume, so you go to Cinder API. Cinder API, the first thing it'll do, it creates a record in the database. It says, the volume has this name and this size, and it's in a state called creating. And then it goes to the scheduler. As we said, that needs to find a place for the volume to reside. So the scheduler, so that goes on RPC. The scheduler chooses some backend. And then it'll update the database as well with the backend that it chose. And then it'll send another RPC to Cinder Volume. Cinder Volume will do all sorts of things like update the quota and I don't know what else. And then it'll call the driver. The driver will actually contact the storage to create the volume on the storage. Then it goes back to Cinder, the generic part of Cinder Volume, which will finalize things and then update the database to say this volume state is now available. And then the user who received the ID at the beginning of what the volume's ID is can poll, do volume get. Okay, he sees it, it's available, great. Okay, so what happens if our scheduler goes down? So, yes, he's getting a little ticked off. Our scheduler goes down. Any operations that were currently being handled by the scheduler, their volumes are now stuck, right? So the scheduler got some volume that was in a creating state. It was working to try to figure out where to put it, and then the Cinder scheduler went down, either the process or the entire node. But what we're left with is the user is doing Cinder get, my volume is still creating, like 10 minutes, 20 minutes, what's going on? And our admin has to go in now and find these volumes that are in creating and figure out why they're not proceeding. And basically, I guess all you can do here is delete them from the database and tell the user, create your volume again. right? If Cinder volume goes down, then things are kind of worse, right? So the user still has that same volume stuck in creating state, but now we might have already created the volume on the storage, or maybe not. So the admin now has some extra work to synchronize the storage with the database. So probably in this case of creating the volume, the admin will want to go to the storage and delete any volumes that are kind of in that stuck state. Another one, Picard is back at work at his terminal. Things are going smoothly. So we'll do an extend volume, which this is typical of many of the Cinder operations where the Cinder API process will do some checks on the volume. So it fetches the volume according to its ID from the database. We're extending the volume size now. So it'll say, okay, its size was 5. Now the user wants it to be 10. That's fine. It's bigger. And we don't need to go to the scheduler because we know which backend is handling this volume. So automatically just send an RPC to that Cinder volume. Again, Cinder volume has some generic duties. It'll update the quota because now we have a bigger volume. We need more quota and things like that. It'll go to the driver, not to create volume on the storage, to extend the volume on the storage. And then we update. So I'm sorry I skipped. In the Cinder API process, before it sends the RPC, it updates the volume state to extending. And at the end, Cinder volume will update the state once again to available. And that's how the user knows that the volume is now extended and ready to use. So now double facepalm. What happens if Cinder volume crashes during this operation? And remember that these OpenStack services are at the same time handling many, many operations. Right? So it could have went down while simultaneously handling some extends and create snapshot and create volume and so on and so forth. So here we have, again, our database with the volume stuck in extending state and the user getting frustrated. We have the admin now has to sync, once again, the state of the database with the state of the storage. But in this case, where in the create volume, the admin had to roll back, or that's usually what he would want to do in create volume because it's easiest to just delete and tell the user to create again. Here, the user might have data there. He can't delete the volume, obviously. The admin also can't shrink the volume back to its original state because the Cinder API doesn't support shrinking. Not all storages support shrinking. So in this case, the admin will have to see what the state of the volume is on the storage and then sync the state of the database according to what the storage is.
So now what you can see is that I have my 5-node cluster using four of them. And since we're working with console, so I can run console members to see which nodes I have. If I make it a little bit smaller, I don't know if you'll be able to see, but so we have nodes 0, 1, 2, 3, and 4. Yeah. No, that would be awkward. I'll be fine. Thanks. And I can also run. So if we're more familiar with Nova, I can run Nova Managed Service List. Well, you can sort of dig out here the nodes 0 to 4 that we have in the cluster. So hoping you believe me now. So I said that one of the things console helps us with is service discovery. So say I want to resolve the name mysql.service.straddle, which is supposed to get me to our MySQL database. And I said we're working with a Galera cluster in this specific setup of 3 nodes. So you see the DNS is resolved to 3 different IP addresses. And the fun thing is, as fun as it could be, if I run it a few times, these entries are randomized. So this gives us inherent load balancing within the 2. I can also query the MySQL database, since it's Galera, to show the cluster size of the Galera database. And you see that it has now 3 nodes running Galera. On the other hand, if I look at, if I try to resolve OpenStack Cinder API, I have it running only on my controllers. This is the IP of this specific machine here. So the next thing I want to do is use Cinder API to do Cinder create. So let's create a volume of 2 GB size. You see it's creating, and now I can run Cinder list. And excuse the window, but you can see the volume is available now in Cinder. Another thing I can do is I can query the database for the same thing, because one of the things that Cinder did for us was write it in the MySQL database. So I'm querying the Cinder database for the created at, ID, and size from the volumes table. And as you can see, I see the same ID as I have above. So far not very impressive. What we can do now is, since all the nodes know that when they want to talk to Cinder API, they go to OpenStack Cinder API.service.straddle and not to some IP or something, I can run this Cinder list from anywhere in my cluster. Come to my screen at the office, you'll see it's nice and white. And now we're going to start being a little nasty to this guy. So what I want to do now is go to the controller and systemctl stop MySQL. So I'm basically killing the database instance running on this controller, and we're still supposed to have two other instances of the database running. So if I query the database, you can see that the Galera cluster size now is 2 because one of the instances died. And as you can see, I can still query the database for the same query I did before. And you can see the data here. So even though my database instance is killed there, I still have 2 other ones running, and they're synchronized and they have the same data. Another thing I can do, obviously, is Cinder list from any of the nodes here, and you can see the same list as before. Okay, so now we were able to kill the database and have 2 other running. Actually, another thing we can show here is that if we try to resolve the name, excuse me. So you see now the DNS automatically resolves it only to the 2 nodes that have the database running. So this is all happening automatic by the health checks the console is running in the background. Console uses the results of these health checks to update the registry, the key value store which is distributed, and the local DNS servers on each of the nodes. So what I'm going to do now is I'm going to stop the Cinder service. So OpenStack Cinder API. Okay, so Cinder is dead now, and if I try to resolve it, you see there's no response because the service is down, I can't access it. But what I'm going to do now is I'm going to bring it back up on a different node because we have HA, right? And the OpenStack services are designed to be stateless. The only exception here are all the terrible cases that Avishay described in the previous slides. But if I started here, OpenStack Cinder API. So it started here, and if I do that same dig command as before, now I have an IP resolution. It's the IP of this guy here. And again, from anywhere in the cluster, let's take this node, for example. I can do Cinder list and see my volume here again. So basically, this combination of console as an enabler for HA together with the different components as the database, messaging, the actual storage backend, give us the ability to achieve high availability on the cluster. So I think that was most what I want to demo, and now Avishay will continue.
Thank you. Okay, so let's sum up with how do we deploy Cinder? So today you can run Cinder API active-active, except for one thing. If I go back here, so I mentioned that, for example, extend volume will fetch the volume from the database and do a few checks and then update the state. So currently that update isn't atomic. So if you have two concurrent operations on the same volume, it could get you into a bit of a mess. But that is currently being taken care of for Liberty. But as of Juno, that's a bit of a problem. If you're worried about that, you can have your load balancer, for example, route requests based on the volume ID and then have local locks to make sure that you don't get into trouble. But again, that's only if you have concurrent accesses on the same volume. Cinder Scheduler is okay for active-active. And Cinder Volume currently can only be run active-passive. That's because it uses local file locks for some of the operations. Some of the drivers use the local file locks as well, which is kind of not nice, but that's also something being looked at for Liberty. In addition, and that's the services. So you can run Cinder API active-active, with a little asterisk about the atomic updates. Cinder Scheduler is fine. Cinder Volume active-passive, so if it goes down, you'll have to bring it up and maybe have a little bit of downtime. And then we have the database. So as I mentioned in the previous slides, where things, services fail and things in the database get out of sync with the storage as well. So there is some manual cleanup to be done by the admin or by some external software that can track all these things and fix it. There's also another thing to be aware of. Anything that gets deleted from the database doesn't actually get deleted. It's just marked as deleted. And once in a while, you have to go and actually delete the things that are marked as deleted. Otherwise, your database might explode. So in Juno, there's now a Cinder manage command where you can purge all of the old records, and that's very highly recommended to run periodically. So what's going on in Kilo? So Kilo was released about, I guess it's not that fresh anymore. It's about a month and a half. A lot of work was done on driver stability. There's now a continuous integration for all of the drivers. So what that means, until Kilo, basically the only thing that the Cinder's continuous integration ran on was the LVM driver. Now each storage runs its own CI. So basically, you upload a new patch to Cinder. That patch will be run on all of the different storages. So IBM has a server in their labs connected to real storage that runs that patch with all the tests, and HP has on their storage, and EMC, and then. And then you get some result at the end that says, okay, it passed on all of the storage, and that's a good thing. Your patch might have broken some storage driver, which in the past would have just broken it, and nobody would know until either the vendor did some testing, hopefully, or until someone deployed it in the field and ran into a bug. So now we can know that right when the patch gets submitted. Multi-attach is also a big feature that has been in the works for some time. It landed in Cinder for Kilo, but not in Nova, unfortunately. So while the code is there in Cinder, it's not currently usable. Hopefully in Liberty that will get better, so the code will be merged into Nova as well. And there is also support for incremental backups and some additional functionality for consistency groups. And if we look into Liberty, I raised a few issues with recovery and processes going down. So the community is aware of all these things. There are some things that are more easy to fix, like the atomic updates that I mentioned. I'm not sure if the patches are already emerged, but I did see some patches submitted for that. But things like recovery, for example, Cinder volume goes down, and now comes back up and you have to sync the state between the storage. That is not yet, there's no real roadmap for that yet. There's a project called TaskFlow, which is meant to do that, but it's kind of mixed feelings from the developers about you have to rewrite the code, first of all, in a different paradigm. The debugging has been difficult. The traces have been difficult to read. And Cinder is kind of moving forward with TaskFlow, but not really wholeheartedly. They are adding, the key feature is writing to the database at every step so that when you come back up, you know where the operation was at when the process went down. Unfortunately, the Cinder flows are kind of complicated, and you'll have 10, 15 updates to the database during each of these operations, which can kind of greatly slow down your system. So that's an open question in the community.
So just one last comment. Sorry for barging in. I was asked, so it's an interesting point to bring up. Our whole testing infrastructure and the demo that you saw was part of it. We basically brought up a test cluster of 5 machines. We're working on an infrastructure called Rack Attack. It's open source. We've put it out to the community, so you can look it up on GitHub/StraddleScale. It's basically an infrastructure that lets us dynamically allocate physical servers from our rack and install different root file systems on them, deploy them very quickly, and I mean within minutes or less we're up and running with a cluster that's gone through installation, and we can run our tests on them. So you're welcome to try this out, GitHub/StraddleScale.
And that's it. Okay. Thank you very much.